Hello chemistry students, Dr. Tullis here. We are starting on chapter 7, which is chemical quantities, where you will be introduced to the mole, which is Avogadro's number. Let's get started. This chapter's career is looking at the veterinarian. Veterinarians perform lab tests on animals. They vaccinate against distemper, rabies, and other diseases. They prescribe medications if an animal has an infection or an illness. They treat wounds and set fractures, and they perform surgery such as neutering and spaying. We're starting off this chapter looking at the mole. You're going to be able to use Avogadro's number to calculate the number of particles in a given number of moles, calculate the number of moles of an element in a given number of moles of a compound. Avogadro's number is 6.022 times 10 to the 23rd. That tells us how many particles, atoms, molecules, or ions are in 1 mole of a substance. 1 mole of any element contains 6.02 times 10 to the 23rd atoms of that. 1 mole of a molecular compound contains 6.02 times 10 to the 23rd molecules. 1 mole of an ionic compound contains 6.02 times 10 to the 23rd formula units of that compound. 1 mole of an element contains 6.022 times 10 to the 23rd atoms. 1 mole of a molecule contains 6.022 times 10 to the 23rd molecules. You can see the same for 1 mole of an ion contains Avogadro's number in ions, all the way on down. Here are some more examples. 1 mole of aluminum has 6.022 times 10 to the 23rd atoms of aluminum. And you can see it's not just atoms, it's molecules, it's formula units, but 1 mole of anything has 6.022 times 10 to the 23rd atoms, molecules, ions, particles, or formula units. So knowing that, we can write an equality using 2 conversion factors, knowing that 1 mole is equal to 6.022 times 10 to the 23rd particles. So we can say that 6.022 times 10 to the 23rd particles is equal to 1 mole, and we can flip it around and we can say that in 1 mole there's 6.022 times 10 to the 23rd particles. We can then use Avogadro's number as a conversion factor to convert between moles of a substance to the number of particles or ions, atoms, molecules, formula units that it contains. For example, let's convert 4.00 moles of iron to atoms of iron. I'm going to start with what I'm given, that 4.00 moles of Fe. Be sure that you label, because we want to make sure that we write what we want over what we've got, and that what we've got are units. Moles of iron and moles of iron are diagonal from one another to cancel out. We then can type in our calculator 6.022 times 10 to the 23rd times 4. I started with 3 significant figures, so I'm going to end with 3 significant figures. And we should get 2.41 times 10 to the 24th atoms of iron. We can use Avogadro's number to convert between the number of molecules to mole. So if we convert 3.01 times 10 to the 24th molecules of carbon dioxide to moles of carbon dioxide. So I'm starting with what I'm given in my problem. What do I want? I want moles of CO2. And for every 1 mole of anything, there's 6.022 times 10 to the 23rd of it. So 3.01 times 10 to the 24th times 1, which is itself, divided by 6.022 times 10 to the 23rd, and we should get to 3 significant figures, 5.00 moles of carbon dioxide. Let's look at a sample problem. What if I have 1.75 moles of carbon dioxide? And it shows us that here's a carbon dioxide molecule, 1 carbon and 2 oxygens on either side. This solid carbon dioxide is known as dry ice. Let's write a plan to convert from moles to particles. Again, I'm starting with 1.75 moles of carbon dioxide. Moles of carbon dioxide. So I have to have moles of carbon dioxide on the bottom. And what do I want? I want molecules of carbon dioxide. So wherever we see the molecules or the atoms or the ions or the particles, that's 6.022 times 10 to the 23rd for every 1 mole. I started with 3 sig figs. I need to end with 3 sig figs. You should get 1.05 times 10 to the 24th molecules of carbon dioxide. Let's look at moles of elements in a compound. Let's look at aspirin. Aspirin has a chemical formula of C9H8O4. Let's look at how many atoms of each element are in 1 molecule of aspirin. Well, that 9 goes with the carbon, so there's 9 carbon atoms, there's 8 hydrogen atoms, and there's 4 oxygen atoms. The subscripts of the formula of aspirin also tell us the number of moles of each element in 1 mole of aspirin. So 1 mole of aspirin contains 9 moles of carbon atoms, 8 moles of hydrogen atoms, and 4 moles of oxygen atoms. And knowing this, we can write some ratios. If I look down here, the chemical formula subscripts right here shows us that there are 9 atoms of carbon in 1 molecule of aspirin, and 8 atoms of hydrogen and 4 atoms of oxygen. But now let's say I had 1 mole of aspirin. That means in 1 mole of aspirin I would have 9 moles of carbon, 8 moles of hydrogen, 4 moles of oxygen. That allows us to write all of these conversion factors. I can say that in 1 mole of aspirin there's 9 moles of carbon. And I can flip-flop that. Same with the hydrogen. Notice that this is just the reciprocal of it. And oxygen, that's the reciprocal. So let's say how many moles of carbon are present in 1.50 moles of aspirin. So I need to convert from moles of the compound to moles of an element. I'm going to start with what I was given, 1.50 moles of aspirin. What do I want? I want moles of carbon. What have I got? I've got moles of aspirin. And we know that there's 9 moles of carbon for every 1 mole of aspirin. I started with 3 sig figs and I'm going to end with 3 sig figs. You should get 13.5. Take a minute to look at the chapter review and make sure that you understand the learning goals. Our next section is looking at molar mass. Notice here that I have 1 mole of sodium chloride and 1 mole of potassium chromate. And notice that even though I have the same amount of them, they have different masses. It would be like if I said I had 1 dozen pencils and 1 dozen cars. I have the same amount of each, but 1 dozen pencils would definitely have a smaller mass than 1 dozen vehicles. Same here. And obviously 1 dozen pencils would take up less space than 1 dozen cars. I've got 1 mole of sodium chloride and I have 1 mole of potassium chromate. Notice that there's still the same amount, but they weigh different. So given the chemical formula of a substance, you're going to be able to calculate its molar mass. A single atom or molecule is much too small to weigh, even on the most accurate balance. In the lab, we use a balance to weigh out Avogadro's number of particles for 1 mole of a substance. For any element, the quantity called molar mass is the quantity in grams that equals the atomic mass of that element, and we find that on the periodic table. We are counting 6.022 times 10 to the 23rd atoms of an element when we weigh out the number of grams equal to its molar mass. The molar mass of an element is obtained from the periodic table. Notice that when we see silver, for example, we know this top number is the atomic number, which is how many protons it has. But down here on the bottom, this number, the average atomic mass, we use for the molar mass. And in our last lesson, we learned that there's 6.022 times 10 to the 23rd atoms in 1 mole of carbon. Now we're going from moles to mass, and we know that 1 mole of carbon has a mass of 12.01 grams. We see that on the periodic table. Notice that sulfur, 1 mole of sulfur has a mass of 32.07 grams. So to determine the molar mass of a compound, you multiply the molar mass of each element by its subscript in the formula, add the results and round to the nearest hundredth of a gram, or use at least 4 significant figures for the calculations. For example, if I have H2O and I want to know the molar mass of this compound, I would look up on the periodic table and find hydrogen. Hydrogen has a mass of 1.008, and I would multiply that by 2 because there's 2 hydrogens. And then I would add 1 oxygen because there's not 2 or 3 or 4, there's 1. And oxygen is 15.999, and then I would get this total. It's going to be really close to 18. I think it's 18.015 grams for the molar mass of water. Let's calculate the molar mass of lithium carbonate, which is Li2CO3. It's used to treat bipolar disorder. First, we need to obtain the molar mass of each element from the periodic table. So I've got the lithium, carbon, and oxygen. So we've got the lithium is 6.941, carbon says 12.01, Oxygen is 16 grams. And remember, when I look at the periodic table and find those masses, it's always for 1 mole of those elements. But I don't have just 1 mole of each of those, do I? In Li2CO3, I have 2 lithiums, I have 1 carbon, and I have 3 oxygens. So I'm going to take those molar masses and multiply it by how many there are of it. Notice that my units cancel out diagonally from one another. I have 2 moles of lithium, and so I have to say that 1 mole of lithium, diagonal from it, has the mass of 6.941 grams. That cancels out my moles, leaving me with grams. And then 1 mole of carbon times 12.01 grams of carbon per 1 mole. And then 3 moles of oxygen. And each oxygen, your periodic table might say 15.999. It's okay if you round. That gives me each of these 3 individually. And then to get the total molar mass, we just add all of them up. 73.89 grams of lithium carbonate for 1 mole of lithium carbonate. That's its molar mass. Let's look at some quantities of other substances to see what 1 mole looks like. Here's 1 mole of sulfur. Here's 1 mole of iron, 1 mole of salt, 1 mole of potassium chromate, and 1 mole of sucrose. Sometimes it's hard to look at these and go, that is not the same amount of each of those. We can see with our eyes that it's not the same amount, but it is. Again, think about having 1 dozen instead of 1 mole. 1 mole is 6.022 times 10 to the 23rd atoms or ions or molecules. Just like saying 1 dozen is equal to 12 objects. I could have a dozen bananas. I could have a dozen apples. They're going to have the same number of each, but obviously they're going to weigh different. I have 1 mole of sulfur versus 1 mole of iron. Look at the weight difference between those. Take a minute to look at the learning goals to make sure that you're comfortable with this section.